just gonna start the recording now. Okay. Aamen, do you think we should start? Like officially?
Again, can you repeat that again?
Okay. So hi guys, welcome to Set Theory. Do you wanna go to the next slide so we can introduce ourselves? Okay. Next slide again. Okay, yeah. So hi, my name is Liza. You might have seen me in Discord already, but I am a senior in Lee High School, which is a school in California. I'm passionate actually about everything computer science, and I've been introduced to set theory through a math computer science course this past summer. So I'm actually kind of new to it too, and I'll be learning along with you guys. And I'm really excited for the next few weeks.
And I'm Aamen, a 12th grader at STEM schools in Egypt. And I'm mostly interested in pure mathematics, especially set theory, group theory, number theory, and various other branches of mathematics, actually.
Okay, so we're going to quickly run down how these classes are going to work before we get to the actual content. So obviously we're just going to stick to the Zoom format. It will be the same Zoom link every single week, Thursdays at 5 p.m. PST. So you're already in the right place. In every class, we're going to plan on recapping a bit of the content that we covered last week so that everyone gets a bit warmed up and caught up. Cover some new content, and we have like a whole syllabus laid out and stuff. And then we'll all have a bit of practice at the end so that we can make sure we understand what we're covering that day. So what is set theory? Like this weird thing that we've been talking about, what is it? Can you go to the next slide? Yeah, so set theory is basically the foundations of all mathematics. It's like a common ground that was established relatively recently to make sure that everything is defined in the same way. So it basically was a way to redefine old concepts like natural numbers and functions and relations and stuff that you guys probably already know from regular math in a standardized method.
So in order to start set theory, there must be certain definitions that we need to be introduced to. So first, we work in what we call axiomatic systems. So axiomatic systems are basically a group of definitions. You start with certain definitions, so you define your terms that you're going to use, and you start also by a set of axioms. So axioms are just the obvious facts that do not really need a proof. So these are just tautologies or things that are taken for granted, and so you want these two to be as little as possible. You don't want a lot of terms and a lot of definitions, and you don't want also a lot of axioms. And so the fewer of these, the better the axiomatic system is, and and that's what basically set theory or how set theory will work. We will start building an axiomatic system in order to explain all of mathematics with as little as possible of definitions and axioms. So in order to describe any system, we describe systems in one of two notions: truth and consistency. So, and these terms should never be confused together. So a system, for a system to be true, it means that system cannot be perceived otherwise. So there will be a contradiction if this was not the case, like 2 plus 2 equals 4. It cannot be in any other way. Whereas consistency means that it's logically coherent. So it just does not contradict itself, nothing more. But this does not mean that it is true. It might be still false, but it does not contradict itself. It might contradict reality, but not itself. So this is consistent, but truth means that it contradicts reality. It cannot be true. Even if it's logically coherent and does not contradict itself, this might be contradictory to reality itself. So that's the difference between truth and consistency. And so we usually describe these axiomatic systems in formal language, especially for mathematics. So the mathematical formal language is just a set of or a system of symbols and structures in which we express statements in. So these are examples of these symbols, and we'll go through each of them. So assuming that P and Q are any statements, so this symbol means not P or the negation of P. So this means uh, the opposite of P. So because of obviously P is it's either true or false. So not P is the negation of P. It's opposite. This symbol means and. So whenever we use this symbol, we mean and Q. This symbol means or, so this would mean P or Q. This is the entailment relationship, so here P entails Q, or if P then Q. This is P if and only if Q, and this is just simply the double implication, so P implies Q and Q implies P. And this last symbol, like the belong, but in the opposite side, is called such that. So P such that Q. So Q is usually here a condition that's based on P. So we can literally write any statement in this formal language. So, for example, if we say that P represents its daytime and Q represents its nighttime, then P or Q is true. So it's either day or night. So, but it cannot be both. So P and Q must never be true. But P or Q is true. So it's either day or night. And for another example, if P represents there is life on planet X, and Q represents that planet X is planet Earth, then Q here entailing P is always true, but P entailing Q is not always true. So, and you can basically do this to any English statement or any statement in general. You can put it in this formal language. You can describe it in this formal language. So here is just an example or sort of a quick exercise. So I want each of you to try and describe the truth or consistency of each of the following systems. So system one, it's saying that A entails B, and B entails C, and C entails D. So system two says that A entails B, B entails C, and C entails not A. So here, if A is true, B is true. If B is true, C is true. If C is true, then A is false. And the last system is just the same as the first system, but here the difference is that here you know for sure that A is true. So if you can just type what you think of the truth and consistencies of these systems. Okay, so Lisa, if you can check the chat if someone typed or something.
Yeah. Oh, so if you guys would just put in the chat, you can private message either of us if you want to. Do you think that system one is true, and do you think that it's consistent? Okay, so the arrows, Aamen mentioned this really quickly earlier, basically just mean that there's a relationship between the two statements. So if A and B are two statements, they can either be true or false, and there's an arrow in between them, that means that if A is true, then B is true. So in the earlier example, we said that if a planet is Earth, then that planet has life on it. So A is the planet is Earth, and B is the planet has life on it. So it's basically just saying that I have these two statements, and I'm saying that if this one is true, then this one must be true. So in system one, you can see that we're basically chaining a bunch of them together. We're saying that if A is true, then B is true. If B is true, then C is true. And if C is true, then D is true. So do you think a system or like a hypothetical world where we have these four statements and they all imply each other, do you think that system could exist? Is it true? Aamen, do you want to like repeat what our definition of truth was?
Okay, so for a statement to be true, it must be not perceivable in any other form. Like 2 + 2 = 4. It cannot be in any other way. So if you just make any other answer to this, so if you say 2 + 2 = 5 or equals 3, you soon arrive at contradictions. So 2 + 2 cannot be otherwise other than 4. So that's what it means for something to be true. On the other hand, consistency means that the system does not contradict itself. Because it can be just totally unreal, but just does not contradict itself.
Could you give an example of something that is consistent but not true?
Something like a unicorn. A
Yeah.
unicorn, it does not contradict itself. It in itself does not. There's nothing in the unicorn that forbids its existence, even though it contradicts reality. It cannot exist because of reality, but it does not contradict itself. So,
Yeah. So like the statement that all unicorns have blue hair, I can just tell you that, and you have no way of contradicting me because you cannot give me an example of a unicorn that doesn't have blue hair. So it can be consistent. There's nothing inherent about the statement all unicorns have blue hair that means that I'm telling a lie. But you know that it's not true because unicorns don't exist. You just can't prove it.
exactly.
So, with that in mind, do you think that the first system, if that was a statement that someone said to you, is it consistent? Is it true? We're already getting an answer saying that system one is false.
Mm. System one is false.
Is it false?
No. So
Yeah.
system one is consistent, but not necessarily true, because A might be false. So A might be false, not true. Even though all these are implications, but A might be just false. So this system is consistent. It does not contradict itself, but it's not necessarily true. So this second system is not consistent and hence certainly not true, because here you started with the premise that A is true and reached the conclusion that A is not true. And this can never coexist. So in a system, a thing cannot be both true and false at the same time. So system 2 is inconsistent and also not true. System 3, however, is both consistent and true. So first, it's consistent, it does not contradict itself, and here you know for sure that A is true. And so this whole system is true because you know that A is true, and A proves that B is true, B proves that C is true, and C proves that D is true. So all the statements here are true in general. So system 3 is both true and consistent. System 1 is only consistent and might be true, but not necessarily true. System 2 is just false and inconsistent.
So if we had to group all of the statements into like say one big Venn diagram, all true statements are consistent, but not all consistent statements are true. And there are statements that are neither consistent nor true. So if you guys, I wish we had some kind of diagram to show you, but if you guys imagine like a big circle that basically encompasses all the statements I can say, like I can state anything and it fits in this circle. There's a smaller circle that says some of these statements are consistent, which means there's no way to disprove them. And then a smaller circle within that that says some of these statements are true. Does that kind of make sense? Okay, thanks.
Okay, so the next concept that we'll use, that we'll discuss, is the truth table. So the truth table is just a method in order to represent the relation between truth values of more than a statement. So for example, this is the simplest form of a truth table of the relation between P and not P. If P is true, then not P is certainly false. And if P is false, then not P is true. So basically, if something is true, its opposite cannot also be true. So if a thing is either true or false, it cannot be both at the same time. And so here, if P is true, then not P is false. That not P is false. If P is false, then not P is true. So these are more examples. So you have two statements, P and Q, and here you want to discuss the relation of P entailing Q. So if both P and Q are true, then this is true. If P is true and Q is false, then this is false. And in all other cases, P until Q would be considered true. So this might seem a little counterintuitive, but since we are already discussing set theory and since we aim to redefine everything, so that's basically a different kind of entailment. So we are literally redefining the relationship between P and Q, because all in the by our intuition or what we understand from this statement that if P then Q, but this statement does not tell us of what if not B. So it does not tell us if P is false what happens. It only tells us what if P is true. But and that's why we consider that if P is false, we'll just consider this relationship to be true. So we are basically just redefining this term in order to suit more of mathematical purposes.
So
Another example is P. You want to say something?
I was gonna quickly give an example of like that idea that if P is false, then we're just assuming that the statement is true. If I'm going back to the unicorn example, that's basically saying like if I say that I have an object, if that object is a unicorn, then it is blue. So that is my statement. That is what my P entails Q statement is. But if the object that I give you is not a unicorn, then you can't say that it's not a blue unicorn. We're assuming that the whole statement I said is true because all I said was that if it is a unicorn, it is blue. Does that? I hope that makes a bit more sense. Basically, all you need to remember is that if you see a P entails Q statement, you need to know that as long as P is false, the whole statement is true. If P is true and Q is true, then the statement is true. It's exactly as I stated to you. It's like intuitive. If P is true and Q is false, then I've just lied to you. Like if I give you a unicorn and it's not blue, then I've lied to you. The statement was false. Yeah.
The second example of a truth table would be P, Q, and P and Q. So if you have P is true and Q is true, then P and Q is true. If you have P is true and Q is false, then P and Q is false. If you have P is false, Q is true, then P and Q is false also. And if you have both are false, then P and Q is false. So basically what P and Q tells us is telling us that both must be true. So in any other case, P and Q is false. So if just one of these is false, it's sufficient to say that P and Q is not true. Even if just one part of it is true, this does not prove that the other is true. So in order to make P and Q true, you must have P to be true and Q also must be true. So I hope you get this.
And one more really quick note. Well, two quick notes. If you guys have questions at any point, because we're going through this really quickly, please don't hesitate to DM me because I'm staring right at the chat and I'm answering questions. And also, I don't know if you guys have any experience in computer science, but there are actually symbols and relations for this in computer science that you would learn in an introductory course. So, for example, the negation symbol. I'm really sorry if you guys don't know what I'm talking about, and if you don't know what a boolean is, then just phase out what I'm saying right now. If you do know what a boolean is, then a boolean is equivalent to a statement. If I have a boolean labeled P and I put an exclamation point next to it, it's negating it, right? So that's basically what we were showing in the earlier table, where if I have a statement and I put the negation symbol next to it, then it's basically the opposite of it. I'm switching the value. If I have a statement that's true and I have the negation to it, it becomes false, and vice versa. Just the same way there are and symbols, Boolean operators in computer science. So if you guys already know that bit of computer science, then you can easily relate this to what you already know and understand it a lot better. If you don't know what Booleans are, then please disregard what I just said.
So there are some rules in general when we construct a truth table. Because, for example, if you look at this case and you want to evaluate the truth value of A or B or C, so there are many cases to consider. So here there are 8 possible combinations out of these 3 statements. So you want to make sure that you consider every single case and every single case only once. Okay, so we follow a certain rule while constructing our truth table, and this rule simply restricts when we recycle. So first is how many how many statements, how many times I consider A to be true before I consider it to be false. So if you notice here, you'll find that true is repeated 4 times and then false is repeated 4 times. Here, true is repeated twice, then false twice, then true twice, then false twice, and at last here it cycles every 1 time. So true, false, etc. This method ensures that we consider all the cases. And so the general rule is so that here the first variable cycles every 2 power 0 times. So I start at t. So after 2 power 0 times or just once, I switch to false. After 2 power 0 or 1 time, I switch back to true and then back to false, back to true, etc. till I reach the end of the table. The second variable is 2 power 1. So it switches every 2 times. So true and then true again, and then false, false again, and then true, true again, and then false, false again, and then 2 power 2, and etc. So you just keep adding a power of 2. So if you have one more variable, you have 2 power 3. So after 2 power 3 times, you consider the true case. You start considering the false case 2 power 3 times, etc. Of course, the output does not have a role because it depends on your inputs. So if you look at this output, you find that it does not really follow any rule because it just depends on the truth values of these statements. So here, for example, we are considering A or B or C, and it's always true unless the three statements are false. So, okay, so bearing this in mind, we'll just go for just a couple of riddles applying the truth table. The truth table will help, although you do not necessarily need to apply, but it will help very much to visualize things and such things. So here's the first riddle. I think you all can see it, right? So it just says that four of your friends drank either the truth or lie potions at random, and so the one who drinks the truth potion always says the truth. The one who says the drinks the lie potion always says a lie. He never said the truth. And so the following statements are made. So person A says, "If I lie, so must be." Person C says, "There's at least one liar," and person D says, "A is lying." So here person B did not say anything at all, but you know for sure that if B said the truth, then C must be lying. So that's what you know for sure. So try solving this riddle and try figuring out who drank the lie potion, who drank the truth potion, etc.
And we're gonna spend around 5 minutes on this. It's not that strict. And if you guys have ideas as you go that you think would help others and you can make it a bit collaborative, feel free to put it in the chat. If you have any questions, feel free to put that in the chat. We're just gonna sit here. Okay, I can see that some of you guys are putting in answers and PMing me, which is great, and I really like to see your opinions. But include your reasoning as well, so we can get an idea. But Diana's here. Okay, it's been about 5 minutes. I think we can move on now.
Okay.
So, guess I go.
So the solution. So I'm going to explain it first in a formal way, and then I will try giving more of an intuition about what it means. So first, the statement of C is that he's saying there exists a P or a statement B that belongs to this set A, B, C, or D, so that B is false. So basically, what he's saying that one of these statements, A said either said by A, B, C, or D, must be a lie. So one must be lying. So if we assume that C is lying, then he will be saying the truth because he said that at least one is lying. But if he's lying, then he's saying the truth because he will be the liar then. And then so the only logically coherent case would be that C is saying the truth. Because if he was saying the lie, then he would already be saying the truth. So in all cases, C is certainly saying the truth. I hope that you get that. So from this point, we can, if we look back, this we know that for sure that if B said the truth, then C must be lying. So we know that B entails not C. So that's in the formal way. So here we will put the truth table for P, not C, and P entails not C. So that's just the basic implication truth table, the true, 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 false, false, and then in all other cases that where P is false, then the statement is true. So first we know that not C cannot be true because we know that C is true. So first we know that these two cases are refused, these two rows in which C would be false, but we know that this is not the case. So based on our first conclusion, we can exclude the first and the third rows, and so it's either this or that. But we also know that B entails not C, so that's what that's our basic premise that if B said the truth, then C must be lying. So we know that this statement is true. So we can exclude the second row also, because here it said that the statement is false, although we know that it's true. And so the only possible case left would be the last row, which means that B must be lying. B is saying a lie. So that's the only logical coherent case. And from this, we can conclude that that first C is saying the truth, and B is must be lying. So did you all get that, or is there a problem? So going continuing on with this riddle, we can start considering cases for A and B. So first, that what the statement is saying that if I lie, so must be. So what A is saying, not A implies not B, right? So that's if we are going to translate it into the formal language, not A implies not B. Okay. So we are going again to construct this truth table. So the true, 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 false, false, and the other two cases like the normal implication table. Well, first we know that B is just not true. So we know that B is lying. So not B is true. So we can exclude the second and the fourth rows because if not B is false, then B is true. But we know that B is not true. B is lying. So we can exclude the second and the fourth rows from this truth table. The second part is a little tricky. So we want to understand that this statement is equivalent to A. Not A implies not B is the same as the statement A. Why? Because what A is saying that if I lie, so must B. So that's the statement of A. What A is saying, not A implies not B. So actually, this must have the same truth values as A, or the opposite truth values of not A. I hope that you get that part. Because so here from this we can exclude any way where these two are the same. So we can exclude the first row. So this cannot be the case because here this statement is equivalent to A, and this is not A, and here they both cannot be true. So the first row is also excluded, and so that leaves only the third row to be possible. So not A is false, which implies that A is true. So A must be saying the truth, and then when we go back, we find that D is saying that A is not saying the truth, and so D must be lying. So just the solution would be that C is saying the truth, B is lying, A is saying the truth, and D is lying. So If you have any problem or if there are any parts that you don't get it, just type in the chat. So just wait for about a minute before I go to the second riddle. Okay, so I think I'll just go for the second one. And if there is any problem or if there anything that you just did not get, you can just immediately type in the chat. Okay. So the second riddle, it says the same idea that four of your friends drank the truth or lie potions at random, and they say the following: Person A said the same statement. If I lie, so I must be. C said the same statement. There's at least one liar, and D is lying. Says A is lying. So the only difference is that person B this time made a claim, and this claim is if I say the truth, then C lies, or B implies not C. So you'll just have some time to think about this riddle, I guess.
And try and apply the same strategy that we showed for the last one. Like, try and convert these statements to mathematical logic, and then think about, do any of them contradict? And if we do single out just a few that we're coming down to, try thinking of it in terms of a truth table, and crossing out the answers that you know are wrong, so you can come down to one answer. Can more than one person drink the lie potion?
Mm-hmm.
Yeah?
Oh yeah.
Okay. Okay, I think we've got some ideas going, but Aman, do you want to show the solution now? Because we're hit 5 minutes.
Okay. So the argument for C is just still the same as the first riddle. C must be saying the truth. And this is because he says that there's at least one liar. So if he was that liar, then he'll be saying the truth also. So it's just the same logic that we applied in the first riddle. Here things are a little different from the first riddle. So first, going back, the statement of B is that if I say the truth, then C is lying. So what it's saying that B implies not C. And so here it's also like the previous time. He B this is equivalent to the statement of B. So the B implies not C is actually equivalent to B. So first, we know that not C cannot be true, so we can again exclude the first and the third um, rows. And then, so we are left with the second and the fourth. But we also know one thing, that this is equivalent to B because this is the statement that B is making actually. So if you go back, this is what B is saying. B is saying that if B is true, then C is a lie. So here this is must be equivalent to B. But in the second and the fourth columns, both are opposite. So both are also refused. So actually this riddle does not have any coherent solution. This system cannot actually be consistent. So that system that you're seeing here in the second riddle does not have any solution and it's not logically coherent. And even though maybe our intuition tells us that this system can have a meaning, or that this statement that person B is saying has a meaning, it's actually meaningless. It does not contribute to the meaning at all. So all the cases are refused. So B can neither be true nor can it be false, and this only implies that the statement of B is literally meaningless within this system or within this context. And that's just why we, in general, in set theory, try eliminating our intuition, because here, although our intuition tells us that this might work or that this might have a solution, there is actually no logical solution. With I hope that you all first understood this point. So, and you can make me stop if there is any point that's not clear, so I can repeat it. Okay. So, but with this in mind, we can conclude that there are systems that cannot be consistent, and so I think we are good to start with naive set theory. So, the first idea of set theory first came in mind on the hands of George Cantor. So he's the one who established set theory as the foundation of mathematics. So as Liza said in the beginning, so there was that problem that every branch of mathematics had its own unique definitions, its own unique axioms, and so everything was almost whimsical. So George Cantor wanted to unite all these branches under just one set of premises or under one set of definitions. And so I came with the first set theory ever, or the first axiomatic system that explains all mathematics ever. Um, and this, in general, does not use the formal language of mathematics, or it just can be expressed in the normal language or the informal language. And I think that naive set theory is the one that we are most used to, or the one that we used a lot in schools and such things. So, just I think these are basic definitions that almost, at least we encountered part of it. So a set is just a collection of any group of elements that share a common property, any common property actually. So this simple means all elements in A or B or A union B. There's A intersection B means that the elements in A and B. There's A difference B element in A not in B, and of course B difference A elements in B not in A. There's A complement or A dash, which means all elements that are not in A, that are in any other set except A. And this simple means all elements in A and B, but not in their intersection. So that's basically A difference B union B difference A. So anything that's in A or in B, but not a shared property among these two. So I think that we almost saw this at point of time, I guess. So yeah, but
Actually,
just
yeah, really quick, out of curiosity, can you let me know in the chat whether you have seen this before in school or stuff, or if this is like all completely foreign to you? Like if these symbols are completely new to you, could you let me know? And you can just PM me if you want. Okay. Okay. So I'm just maybe we can spend a bit more time here before we move on really quickly because I think there are some of these symbols that aren't as common here. Um, the easiest way to think of all of these concepts are in terms of Venn diagrams. So if you think of a set as like a bunch of little statements or things or elements is what we call like any arbitrary thing. That sounds really vague, but just think of a bunch of objects in a collection that share a common property. That is a set. You can think of it as like one circle. If I have two sets, A and B, the union of the two are all the elements that are in A or in B. So we talked about the OR property for Booleans a while ago. It's kind of similar to that. So if I had two Venn diagrams, two circles that are A and B, and I overlap them, then A union B includes all of the elements in A and in B. A intersect B are all of the elements that are in either A or in B. A difference B are all the elements that are in A and not in B. The complement of A are all the elements in the whole world, like you can imagine the curtains in the background, and this is A, then all the elements in the whole world that are not in A, and then the last one is kind of similar to the difference, but it goes both ways. It's the elements that are in A and in B, but are not in the intersect. I'm actually wondering if we might have the time, Aamen, if I pull up like some screenshots and screen share them. Do you think we have the time for that?
Oh yes, sure.
Okay. Just give me a quick sec. Alrighty.
Okay, so should I stop sharing?
No, I can once I open this image up. Okay, one sec. Alright, so you guys can see my screen, right? So you can imagine, this is what I was talking about, the Venn diagrams. If A is a set, like imagine this as a literal circle about with all the elements in A that share the property of A. The union includes all the elements that are in A and the elements in B. This was the symbol that looked like a U, union. That's handy. The intersection are all the elements that are in A and in B. So the overlap of the two sets. This was a symbol that looked like an N. The difference, which is just like A minus B, are all the elements that are in A and not in B. So there are elements, you can see there's an overlap between A and B, but we're not including them in the difference. The symmetric difference is kind of like this, but going both ways. It's the elements that are in A and in B, so the union, minus the intersection, the elements that are in both. So if you were to think of examples, can't think of examples for all of them on the spot, but so say you have like a class of students. They're all of different ages. They all have different names. They might have different genders. And say I have a group that's born in months January to June and months July to December. Like they're two different sets. You have a class, you have all your classmates, and you're grouping them based on what month they were born. The union of these two sets would be everyone born from January to December. So everybody that was born in that year. The intersection, I am going to change my example. I'm sorry. Say that one group is January to June, and the other group is May to December. So the intersection would be the groups from May to June, like the people who fit in both groups. The difference would be the people who were just born in January to May. The symmetric difference is everybody but those people who were born in May to June that were in the intersection. I hope that makes more sense, and all of these symbols and stuff that are kind of hard to remember will make more sense the more we practice with them. But I just want to make sure, in case some of you guys are new to those concepts, before we move on, we kind of get a better understanding of that. I think we're good now.
Okay, so this naive set theory entails few paradoxes, and that's why um, it does not really work so well. And that's not really the axiomatic set theory that we'll be working on, but that's just more of a historical context, and we'll use elements of the counter set theory, but with a little modifications. So the paradoxes that arise from this set theory or from naive set theory are two kinds: the logical paradoxes and the semantic paradoxes. So the most famous of the logical paradoxes is Russell's paradox. So basically asks, does the set of all sets that do not contain themselves contain itself or not? So just to get a little intuition around it, so an example of a set that does not include itself is the set of all cats, for example. So the set of all cats is not itself a cat, so it does not include itself. Okay, the set of all dogs is not a dog, so it cannot include itself. So here he's asking, so does the set of all sets that do not contain themselves contain itself? So is this set a member of itself or not? Because if it is a member of itself, then it does not follow the rule of not containing itself. Then it should not then contain itself. But if it does not contain itself, then it's following the rule, and so then it should contain itself. And so in both cases, you end up with logical inconsistency. So in both cases, the statement is just meaningless. Um, if if the set contains itself, you'll prove that it does not contain itself. If it does not contain itself, you'll prove that it contains itself. So basically, this is just similar to the second result that we faced, where no case makes any sense. All cases are just meaningless, and so this is why there are problems in naive set theory, and that's why it was later modified. That's actually, and so we do not in general work with naive set theory, and we'll consider more on the axiomatic set theory, the more of the formal one. So, is there any problem with anyone who does not get the results paradox? Because I think it's a little complicated or something.
When you say do you not get it, we're not saying that do you have a solution for it. We're saying do you kind of understand why it doesn't make sense, why it's a paradox?
Wait, can you repeat that once more?
So, do you guys understand like what Aamen just said, why Russell's paradox is a paradox, or does it not make sense why it doesn't make sense? Okay. Oh, Aamen, do you want to repeat the explanation for the paradox real quick?
Okay, sure. So, in all sets, a set either contains itself or does not contain itself. Okay. So an example of a set that does not contain itself is the set of all cats. So the set of all cats is not itself a cat, so it's not a member of itself. So you do not have a joint cat that consists of all the cats. It's just so this set does not contain itself. Okay, so so a set as defined in naive set theory is just a collection of anything that of a group of things that share any common property whatsoever. Okay, so here the common property that's put in this paradox is that they do not contain themselves. So any set that does not contain itself, we will add it to our set, to our large set. So you can think of it as a set of sets, and these sets share the common property of not including them, of not being part of themselves. Okay, so he is asking, does the set of all sets that do not contain themselves, so that large set that contains all these sets that are not members of themselves, is this set a member of itself or not? Because if it is a member of itself, then it already broke the rule. Okay, so it does not share the same common property, because for a set to be inside this set, it must not contain itself. But if this large set contains itself, then it should not contain itself. Okay, because then it broke the rule. But if it does not contain itself, then it followed the rule, then it should contain itself. So in either cases, you reach a problem. So you reach the conclusion that it's both inside and both belongs to itself, and and also does not belong to itself. Um, I hope that this made more sense.
Okay, yeah, it seems to be making more sense in the chat.
Okay, of course, you do not have to fully understand it. We'll talk about it more while constructing a more consistent set theory, because we will not just work with naive set theory at all. we'll start constructing a better set theory, um, and so you will more understand why it's a problem as we advance more in set theory. Usually, set theory gets better with practice. So the more you practice it, the better it gets. It's not just you cannot. It's hard to fully understand it in one time, and so yeah. So you should not feel bad or strange that you do not fully get it. It just requires a lot of practice, actually. So the other kind of paradoxes is the semantic paradox. So of course, there are a finite number of sentences that you can form from the English language because English language contains finite words. So there are finite combinations of these words. And so imagine a set that contains all natural numbers that can be described in less than 20 words, okay? So basically we know that there are infinite number of natural numbers and there are finite number of sentences. So there must be at least one of these numbers that cannot be described in less than 20 words, okay? So the semantic paradox here would be the least element that cannot be described in less than 20 words from the English language was actually just described in less than 20 words. So basically, semantic paradox is more related to language, and so it's more of it just simply contradicts the way our language works. So if you count these number of words, so here we just describe this number in less than 20 words, although it should be the least element that is not that's described in more than 20 words. I hope that I hope that this kind of makes.
Oh, because that description itself is less than 20
Anyway,
words.
so this description itself, so if you count the number of the underlined words, it's less than 20 words.
Oh my god, okay.
So I
I'll
hope
admit I hadn't realized that until now.
I hope that this makes sense.
It's insane. Wait, again, if you guys aren't quite understanding why that contradicts itself, why that's a paradox, just let us know in the chat. Okay, I think I think it's good.
So, of course, again, just the same as with logical paradoxes, as when you advance more with using the mathematical formal language, and as we construct the set theory and the system, this will make a lot more sense than this, and it will be easily understood than this, I guess. So I guess we are done. So if you have any questions or something, or if there is anything you want me to re-explain, or if there's any part not clear. So,
And just keep in mind that, like Aamen said, set theory is something that this is normally like a full college course. This takes a long time to process and to wrap your mind around, but the ultimate goal is to make all of maths a lot easier to understand. And if there were things that we mentioned today that went over your head or you feel really intimidated about, don't worry. That's how everybody feels right at the beginning. It's a lot of abstract concepts. And I also know we kind of breezed through those definitions of the different ways to describe sets right before talking about paradoxes. But we kind of just wanted to talk about paradoxes because they're really cool. And we will cover more in detail about those set operations next week. We already have that planned out. Um, so yeah, do you guys have any questions right now? Paradoxes are really cool. Yeah. By the way, Aamen, can you see the chat?
mm,
Oh, okay. Wait, I'll show you how to see it later. We probably can include more riddles later on. It's more like all set theory problems feel like riddles, like traditional riddles that we see.
mhm.
So yes, there will definitely be more practice with them later. Yeah, I'm excited. I don't think there are any more questions, so I think we can wrap up for today.
Okay, so I'll just put a link in the chat. So this is just a form. I hope that you all just fill. Okay.
By
So.
the way, I'm gonna stop the recording. So